All right, let's get started. So let's see, logistical reminder, the class midterm is this Wednesday, and it's 48-hour take-home midterm. And the logistical details you can find at this Piazza post, right? So the midterm will start Wednesday evening. You have 48 hours to do it and then submit it online through Gradescope. And because of the midterm, there won't be a section this Friday. Okay. Oh, and the midterm will cover everything up to and including EM, which we'll spend most of today talking about. Okay. Susie, don't look so stressed. It'll be fun. No. All right, well, maybe. All right. So what I'd like to do today is start our foray into unsupervised learning. So far, I've spent a lot of time on supervised learning algorithms, including advice on how to apply supervised learning algorithms. This pen isn't great. In which you'd have, positive examples and negative examples, and you run logistic regression or something, or an SVM or something to find the line, find the decision boundary between them. In unsupervised learning, you're given unlabeled data. So rather than given data with X and Y, you're given only X. And so your training set now looks like X1, X2, up through XM. And you're asked to find something interesting about the data. So the first unsupervised learning algorithm we'll talk about is clustering, in which given a data set like this, hopefully we can have an algorithm that can figure out that this data set has two separate clusters. And so one of the most common uses of clustering is market segmentation. If you have a website, selling things online, you have a huge database of many different users and run clustering to decide what are the different market segments, right? So there may be, people of a certain age range, of a certain gender, people of different age range, different level of education, people that live in the East Coast versus West Coast versus elsewhere in the country. But by clustering, you can group people into different groups, right? So I want to show you an animation of really the most commonly used clustering algorithm called k-means clustering. And let me show you an animation of what k-means does, and then we'll write out the map and talk about how you can implement it. So let's say you're given a data set like this. So all these are unlabeled examples. So just X plotted here. And we want an algorithm to try to find maybe the two clusters here. The first step of k-means is to pick 2 points denoted by the two crosses called cluster centroids. And the cluster centroids are your best guess for where are the centers of the two clusters you're trying to find. And then k-means is an iterative algorithm, and repeatedly you do 2 things. The first thing is go through each of your training examples. Oh, I'm sorry. Oh, okay, thank you. All right, great. Let me know if it happens again. Okay, right. So you guys saw that, right? So, right, you have 2 cluster centroids. So the first thing you do is go through each of your training examples, the green dots, and for each of them, you color them either red or blue, depending on which is the closer cluster centroid. So here we've taken every dot and colored it, red or blue, depending on which side it is, which cluster centroid is closer to. And then the second thing you do is look at all the blue dots and compute the average, right? Just find the mean of all the blue dots and move the blue cluster centroid there. And similarly, look at all the red dots and look at only the red dots and find the mean, what's wrong with this? Oh, interesting. It's very strange. All right. Apparently, if I keep moving my mouse, it doesn't do that. All right, thank you. And then find the mean of all the red dots and move your red cluster centroid there. So let me do that, right? So the cluster centroids move as follows. To the mean of the red and the blue dots. And this is just a standard arithmetic average, right? And then you repeat again, where you look at each of the dots and color it either red or blue, depending on which cluster centroid is closer. So I'm going to recolor every point based on what's closer. So that's the new set of colors, right? And then the second part of the algorithm was, again, look at the blue dots, find the mean, look at the red dots, find the mean, and then move the cluster centroids over, to that mean, okay? And so, and it turns out if you keep running the algorithm, nothing changes. So the algorithm has converged. So if you look at this picture and you repeatedly color each point red or blue, depending on which cluster centroid is closer, nothing changes. And if you repeatedly look at each of the two clusters of colored dots and compute the mean and move the clusters there, nothing changes. So this algorithm has converged even if you keep on running these two steps. Okay, so let's see. Let's write down in math what we just did. All right, so this is a clustering algorithm, and specifically, this is a k-means clustering algorithm. So your data set now does not come with any labels. And so in k-means, step one is initialize the cluster centroids. Right? I'm going to call them mu1 up to mu k randomly. Right? So this was a step where you plot down the red cross and the blue cross. And when I did it on the PowerPoint, I did it as if we would just choose these as random vectors. In practice, a good way of, actually the most common way to select the random initial cluster centroids isn't quite what I showed, is to actually pick k examples out of your training set and just set the cluster centroids to be equal to k randomly chosen examples, right? So in a low-dimensional space, like a 2D plot, they can do on a diagram, it doesn't really matter. But when you work with very high-dimensional data sets, the more common way to initialize these is just pick, k training examples and set the cluster centroids to be at exactly the location of those examples. But in low-dimensional spaces, it doesn't make a big difference. And then next, you repeat until convergence. Step one is right, so this is a just write this down. So that makes sense. So the two steps you would alternate between. The first one is set Ci for every value of I. So for every example, set Ci equal to either 1 or 2, depending on whether that example Xi is closer to cluster centroid 1 or cluster centroid 2. Right? So just take each point and color either red or blue. And we represent that by setting Ci equals 1 or 2, if you have two clusters, if k is equal to 2. Right? But yeah.
In the notes, this is actually, I think, the L1 norm squared. So is the correct expression?
Oh, the notes say L1 norm squared? From this morning? What notes was sent out this morning?
The ones on the website.
Oh, that's weird. It shouldn't be L1 norm. If it says L1 norm, that's a mistake. Sorry about that. But usually, and it turns out whether you use L2 norm or L2 norm squared, they give you the same answer because the argument is the same either way. But just usually, do a typo in the notes? Oh, I see. Oh, got it. Okay, looks like in the notes we wrote that. Okay, cool. But by default, when we write that norm, we actually we mean L2 norm. Yeah, right. By default, this is the L2 norm of X if it's unspecified. If it's L1 norm, we usually write this. So L2 norm is more common, and with or without the square, you get the same result. Okay, cool. Thank you. All right, so let's color the dots. Paint each dot either red or blue. And then for this, this is, sum through your examples and take all the examples assigned to a certain cluster, right? Assigned to cluster J and set mu J to be average of all the points assigned to that cluster J. Yeah. Oh, sure. Let me see if we can. Nope, that does not work. I don't know if I have a, all right, none of the black markers are working. Is this better? All right, let me try to use this. Is there part of this is unclear? If there's part of this you can't see, I'll write it out more clearly. Yeah, go ahead. Oh, sure. Hi, do we have lights in front? Oh, okay. Got it. Let there be light. All right, awesome, great. That was an easier request to satisfy. That was all. Okay, I just want to let you look at it for another minute. All right, is it okay? Thank you. Oh, right, and this wasn't part of it. Okay, all right, now I can move it up. All right, so it turns out that this algorithm can be proven to converge. Exactly why is written out in the lecture notes, but it turns out if you write this as a cost function, right? So the cost function for a certain set of assignments of points, of examples to cluster centroids, and for a certain set of positions of the cluster centroid. So C, these are the assignments, and these are the centroids, right? So this cost here is sum over your training set of what's the squared distance between each point and the cluster centroid that is assigned to. So it turns out, I won't prove this, a little bit more details lecture notes, but I don't want to prove this. It turns out that on every iteration, k-means will drive this cost function down. And so, beyond a certain point, this cost function can't go any lower. Well, this can't go below 0, right? And so this shows that k-means must converge, or at least this function must converge, because it's a strictly non-negative function that's going down on every iteration. So at some point, it has to stop going down, and then you could declare k-means to have converged. In practice, if you run k-means in a very, very large data set, then as you plot the number of iterations, J may go down, and and just because of lack of compute or lack of patience, you might just stop this running after a while if it's going down too slowly. So that's sort of k-means in practice, where maybe it hasn't totally converged, it's just cut it off and call it good enough. Now, the most frequently asked question I get for k-means is how do you choose k? It turns out that when I use k-means, I still usually choose k by hand. And this is why, which is in unsupervised learning, sometimes it's just ambiguous, right, how many clusters there are. With this data set, some of you will see 2 clusters, and some of you will see 4 clusters. And it's just inherently ambiguous what is the right number of clusters. So there are some formulas you can find online, the criteria like AIC and BIC for automatically choosing the number of clusters. In practice, I tend not to use them because I usually look at the downstream application of what do you actually want to use k-means for in order to make a decision on the number of clusters. So for example, if you're doing a market segmentation, because your marketers want to design different marketing campaigns, right, for different groups of users, then your marketers might have the bandwidth to design 4 separate marketing campaigns, but not 100 marketing campaigns. So that would be a good reason to choose 4 clusters rather than 100 clusters. So it's often, if you look at the purpose of what you're doing this for. I think in the programming exercise, in the homework, you see a image compression exercise where you want to cluster colors into a smaller number of clusters, you implement this. It's actually one of the most fun exercises, I think. But so there you be saying, well, how much do you want to compress the image to decide how many clusters to try to use? Okay, so I usually pick the number of clusters, either manually or looking at what you want to use K-means cluster for. Or you're trying to cluster news articles. Like the Google News example, I think I showed in the first lecture. You say, well, how many clusters kind of make sense for news articles? Okay, all right, that's a question. So, yeah, good.
Is this how we can find those global minima, or can it get stuck in different local minima?
Oh, sure. Well, K-means get stuck on local minima. Yes, K-means just subset to local minima sometimes. And so if you're worried about local minima, the thing you can do is run K-means, say, 10 times or 100 times or 1,000 times from different random initializations of the cluster centroids. And then run it, say 100 times, and then pick whichever run resulted in the lowest value for this cost function. Okay? All right, so you play with this more in the programming exercise. Now, there's a problem that seems closely related, but it's actually quite different when you derive the algorithms, which is density estimation. So let me motivate this. I actually have some time back, had some friends working on a problem, which I'll simplify a little bit, if you have aircraft engines coming off the assembly line, right? And every time an aircraft engine comes off the assembly line, you measure some features of these engines. You measure some features about the vibration, and you measure some features about the heat that the aircraft engine is producing. And let's say that you get a data set, right, that looks like this. Okay, and the anomaly detection problem is if you get a new aircraft engine that comes off the assembly line, and if the vibration feature takes on this value and the heat feature takes on this value, is that aircraft engine an anomalous one? Is it an unusual one? Right? And so the application of this is that as your aircraft engine comes off the assembly line, if you see a very unusual signature in terms of the vibrations and the heat the aircraft engine is generating, then probably something's wrong with this aircraft engine, and you can have your people, have your team inspect it further or test it further, before you ship the airplane, before you ship the engine to an airplane maker, and then something goes wrong in the air, and there's a major accident or major disaster, right? And so anomaly detection is most commonly done, or one of the common ways to implement anomaly detection is the model P of X, which is given all of these blue examples, given all of these dots, can you model what is the density from which X was drawn? So then if P of X is very small, then you flag an anomaly, right? Meaning that, gee, I think something's funny here. And maybe someone should inspect this aircraft engine a little bit further. So anomaly detection is used for tasks like this, for inspection tasks like this. Is used for, many years ago, I was actually working with some telecoms providers, helping out telecoms company on anomaly detection to figure out if something's gone wrong with part of the cell tower network, right? So if one day one of the cell towers start throwing off network patterns that seem very unusual, then maybe something's wrong with that cell tower. Like something's gone wrong. You could send out a technician to fix it. It's also used for computer security. If a computer, say if a computer at Stanford starts sending out very strange, network traffic that's very unusual relative to everything that's done before, relative to what is a very anomalous network traffic, then maybe IT staff should have a look to see if that particular computer has been hacked. Right? So these are some of the applications of anomaly detection. And a good way to do this is, given an unlabeled data set, model P of X, and then if you have very low probability examples, you flag that as a possible anomaly for further study. Now, given this data set, how do you model this? One interesting thing about this green dot is that neither the vibration nor the heat signature is actually out of range, right? Like there are a lot of aircraft engines with vibrations in that range. There are a lot of aircraft engines with heat in that range. So neither feature by itself is actually that unusual. It's actually the combination of the two that is unusual. And so what I want to do is come up with an algorithm to model this. And in fact, we'll come up with an algorithm that can model, maybe a data density looks like this, right? More of an L shape like that. But how do you model P of X with the data coming from an L shape? And it turns out that there is no textbook distribution, right? There isn't, if you look at the simple exponential family model types of distributions, there is no distribution for modeling, right, very complex distributions like this. So what we're going to talk about is the mixture of Gaussians model, which would look at data like this and say, it looks like this data actually comes from two Gaussian. There's one Gaussian, maybe that's one type of aircraft engine that is drawn from a Gaussian like the one below, and a separate type of aircraft engine that's drawn from a Gaussian like that above. And this is why there's a lot of probability mass in this L-shaped region, but very low probability outside that L-shaped region, right? Oh, and these ellipses I'm drawing are the contours of these two Gaussians, right? And so what I'd like to do next is develop the mixture of Gaussians model, which is useful for anomaly detection, and then this will lead us to our second unsupervised learning algorithm. Okay. So in order to make the mixture of Gaussians model a bit easier to develop, let me just use a one-dimensional example where X is in R. Okay. So let's see. So let's say that we get a data set that looks like this. Right. So it's just one row number, so just on a number line, I plotted a few dots. So it looks like this data maybe comes from two Gaussians, right? It looks like, there's some data from this Gaussian, and there's some data from that Gaussian on the right. And if only we knew, right, which example had come from which Gaussian. If we knew that these examples had come from Gaussian 1, which we're going to denote with crosses, and if only we knew, that one's, yeah. Well, actually, this is fine. I'll leave that one there. If only we knew that these examples had come from Gaussian 2, which I'm going to draw with O's, then we just fit Gaussian 1 to the crosses, fit Gaussian 2 to the O's, and then we'd be pretty much done, right? Sorry, and so these are the two Gaussians, and so the overall density would be something like this, right? That's the probability. A lot of probability mass on the left, a lot of probability mass on the right, a little less probability mass on the in the middle. Right? So the overall density, just draw it again, would be low, high, something like that, right? But the reason, and if you actually had these labels, if you knew that these examples came from Gaussian 1, those examples come from Gaussian 2, then you can actually use an algorithm very similar to GDA, Gaussian discriminant analysis, to fit this model. The problem with this density estimation problem is you just see this data, and maybe the data came from two different Gaussians, but you don't know which example actually came from which Gaussian. Okay? So the EM algorithm, or the expectation maximization algorithm, will allow us to fit a model despite not knowing which Gaussian each example had come from. So let me first write down the mixture of Gaussians model. And then we'll describe the EM algorithm for this. So let's suppose that there's a so the term we sometimes use is latent, but latent just means hidden or unobserved random variable z. And xi, zi, okay? So, just blocking. So let's imagine that there's some hidden random variable z, and the term latent just means hidden or unobserved, right? It means that it exists, but you don't get to see the value directly. So when I say latent, it just means hidden or unobserved. So let's imagine that there's a hidden or latent random variable z, and xi and zi have this joint distribution. And this is very, very similar to the model you saw in Gaussian discriminant analysis. But zi is multinomial with some set of parameters phi. For a mixture of two Gaussians, this would just be Bernoulli with two values. But if you're a mixture of k Gaussians, then z, can take on values from 1 through k, right? And if it was two Gaussians, it'd just be Bernoulli. And then once you know that one example comes from Gaussian number j, then x condition that zi is equal to j, that is drawn from a Gaussian distribution with some mean and some covariance sigma. Okay, so the two unimportant ways this is different than GDA. One, well, I've set z to be one of k values instead of one of two values. In GDA, Gaussian differential analysis, we had y, the labels y took on one of two values. And then second is I have sigma j instead of sigma. So by convention, when we fit mixture of Gaussian models, we let each Gaussian have its own covariance matrix sigma, but you could actually force it to be the same as you want. So, but these are the trivial differences. The most significant difference is that in Gaussian discriminant analysis, we had labeled examples xi, yi, whereas y was observed. Right? And the main difference between this and Gaussian discriminant analysis is now we have replaced that with this latent or hidden random variable zi that you do not get to see in the training set. Okay? So, now, wow, actually, you guys are right. These pens are terrible. All right, oh, that one's better. Cool. All right. So if we knew the zi's, right, then we can use maximum likelihood estimation. Right? So if only we knew the value of the zi's, which we don't, but if only we did, then we could use maximum likelihood estimation, or MLE, to estimate everything. So we would write the log likelihood of the parameters, right, equals sum log p of xi, zi, given the parameters. Right? And then you take the derivative, set the derivative equals to 0. I think you guys did this in problem set 1, right? And then you would find that phi j is equal to 1 over m right? Oops. Okay, so if only you knew the values of the zi's, then you could use maximum likelihood estimates, and this is what you get. And this is pretty much the formulas. Actually, these two are exactly the formulas we had for Gaussian discriminant analysis, except we've replaced y with z. Right? And then there's some other formula for sigma that's written in the lecture notes, but I won't write down here. Okay. But the reason we can't use this use these formulas is we don't actually know what are the values of z. So what we will do in the EM algorithm is two steps. In the first step, we will guess the value of the z's, and in the second step, we will use these equations using the values of the z's we just guessed. So so sometimes in machine learning, sometimes we call this a bootstrap procedure, where you guess something, then run an algorithm, you're using your guesses, and then you update your guesses, and then run the algorithm again. Let me make that concrete by writing this down. So the EM algorithm has two steps. The E step also called the expectation step, is set Wij So Wij is going to be the probability that Zi is equal to j, okay? Given all the parameters. And much as we did with generative learning algorithms, right? With generative learning algorithms, we use Bayes' rule to estimate the probability of y given x. And so to compute this, you use a similar Bayes' rule type of calculation. And so this would be right. Oops. Right. Where, for example, this term here, P of xi given zi equals j, this would be a Gaussian density, right? This comes from a Gaussian density with mean mu j and covariance sigma j, right? And so this term here would be 1 over, 2 pi to the n over 2, sigma j, so 1/2, e to the negative 1/2. And then this term here, I guess this would be phi j. That's just a Bernoulli probability. Remember, z is multinomial, right? So z is multinomial with parameters phi. So I guess the parameters phi for multinomial distribution tell you what's the chance of z being 1, 2, 3, 4, and so on up to k. And so the chance of zi being equal to k is just chance of zi being equal to j is just phi j, right? It's just read it off one of the parameters in your multinomial probability for the odds of z being different values, okay? And so, and similarly, the terms in denominator, this term here is from Gaussian, and that second term is from the multinomial probability that you have for z. And so that's how you plug in all of these numbers and use Bayes' rule, use this equation to compute, given the position of all these Gaussians, what is the chance of Wij taking on a certain value, okay? And so to make this really concrete, you remember how, I guess, ones and zeros are the other way. If you were to look at these, if you were to scan from right to left, remember how, you get a sigmoid function, right? Or the sigmoid can be this way or this way, right, depending on the sign. I guess if these are positive examples, these are negatives, you have a sigmoid function like this. And so Wij is just the height of this sigmoid. It's just a chance of, each of these examples coming from either the z equals 1 or z equals 0. And then you store all of these numbers in the variables Wij. Okay? So Wij is just compute the posterior chance of this example coming from the left Gaussian versus the right Gaussian, you just store that in the variable wij. So that's the E step. And you compute the wij for every single training example I. Right? Next, the M step is, yeah.
Yeah, and is it in this case with one picture only also the XI maximization transpose?
Sorry, is this what?
So in the Gaussian, should the first vector be transposed, or are we talking about a case?
Oh, this one. Sorry. Yes, thank you. Yeah. Okay, cool. Thank you. Yes, this is a phone of Gaussian. Yes. Okay. So the E step tells us, we're trying to guess the values of the z's, right? We figure out what's the probability of z being 1, 2, 3, 4 up to k, and we'll store it here. And then in the M step, what we're going to do is use the formulas we have for maximum likelihood estimation. And I want you to compare these with the equations I had above, right? Okay, well, hope you can see. But so these equations are a lot like the equations above, except that instead of indicator zi equals j, we replaced it with wij, right? Which, by the way, is the expected value of this indicator function. Right? Because the expected value of an indicator function is just equal to the probability of that thing in the middle being true. Okay? Oh, and then there's the formula for sigma j as well. That's you can get from the lecture notes, but I won't write down here. Okay. So one intuition of this mixture of Gaussian's algorithm is that it's a little bit like k-means, but with soft assignment. So in k-means, in the first step, we will take each point and just assign it to one of the k-cluster centroids, right? And it was a little bit closer to the red cluster centroid than the blue cluster centroid. We would just assign it to the red cluster centroid. So even with just a little bit closer to one cluster centroid than another, k-means would just make what's called a hard assignment, meaning whatever cluster centroid is closer to, we just assign it 100% to that cluster centroid. So EM is you can think EM implements a softer way of assigning points to the different cluster centroids, because instead of just picking the one closest Gaussian center and assigning it there, it uses these probabilities and gives it a weighting in terms of how much is assigned to Gaussian 1 versus Gaussian 2. And then second, it updates the means accordingly, right? Sum over all the xi's to the extent they're assigned to that cluster centroid divided by the number of examples assigned to that cluster centroid. Okay, so that's one intuition between EM and k-means. And then the second, when you run this algorithm, it turns out that this algorithm will converge with some caveats I'll get to later, and this will find a pretty decent estimate of the parameters, of say fitting a mixture of two Gaussians model. Okay. So this is and so if you are given a data set of say airplane engines, you can run this algorithm, fit a mixture of two Gaussians, and then when a new airplane engine rolls off the assembly line, so after you're fitting the k-means algorithm, you now have after fitting EM algorithm, you now have a joint density for P of x comma z, and so the density for x is just sum over all the values of z of P of x comma z, right? And so a mixture of Gaussians can fit distributions that look like this. It can fit distributions that look like this, right? These are both mixtures of two Gaussians. So this gives you a very rich family of models to fit very complicated distributions. And now that, right, and you can also fit, I don't know, something like this, right? So this is a mixture of two Gaussians. I guess one thin, narrow Gaussian here and one much wider, fatter Gaussian. So a mixture of two Gaussians can actually fit a lot of different things. Can fit a lot, and a mixture of more than two Gaussians can fit even richer models. And so by doing this, you can now model P of x for many complicated densities, including this one, right? This example I had just now. This will allow you to fit a probability density function that puts a lot of probability mass on a region that looks like this. And so when you have a new example, you can evaluate P of x, and if P of x is large, then you can say, nope, this looks okay, and if P of x is less than epsilon, you can flag an anomaly and say, oh, take another look at this airplane engine. Okay? So I kind of just wrote down this algorithm with a little bit of a hand-wavy explanation for how it's derived, right? So I kind of said, if only you knew the values of z and just use maximum likelihood estimation, so let's guess the values of z and then plug that into the formulas of maximum likelihood estimation. It turns out that hand-wavy explanation works in the particular case of EM for mixtures of Gaussians, but that there is a more formal way of deriving the EM algorithm that shows that this is a maximum likelihood estimation algorithm and that it converges at least a local optimum. And in particular, what we'll do is show that if your go is given a model P of x, z parameterized by theta, if your go is to maximize P of x, right? Oh, excuse me. Right. So this is what maximum likelihood is supposed to do. That EM is exactly trying to do that. Okay. So I'll go on in a minute to present this more general derivation, the full, more rigorous derivation of the EM algorithm that doesn't rely on this hand-wavy argument of let's guess the z's and use maximum likelihood with the guess value. So I'll do the rigorous derivation of EM in a minute. But before I do that, let me just pause and check if there are any questions. Yeah.
I'm a little confused as to how the weights correspond to guessing the values of the z's.
Yeah. Maybe, let's see, maybe it'll help to not think of them as weights. I think this is actually the weighting you assign to a certain Gaussian, so that's one intuition, hence the weights. But let me think. What's a good way to explain this? So one way to think of this as Wij is how much xi is assigned to, to the mu j Gaussian. Right? So Wij is the strength of how strongly you want to assign that training example xi to that cluster or to that particular Gaussian. And so this is a number between 0 and 1, right? And the strength of all the assignments, and every point is assigned with a total strength equal to 1, because all these properties must sum up to 1. And so we're going to take this point and assign it, 0.8 to more close Gaussian and 0.2 to more distant Gaussian. And this is our guess for, well, there's an 80% chance it came from that Gaussian, a 20% chance it came from a second Gaussian. Does this make sense?
Do you already just randomize the z's, or is this determinate z's? Maybe that's my confusion.
Oh, I see. So let's see. So when you're running the EM algorithm, you never know what are the true values of z, right? You're given a data set, so you're only told the x's. And far as we know, these airplane engines were generated off two different Gaussians. Maybe there are two separate assembly processes, one from plant number 1, one from plant number 2, and maybe they actually operate a little bit differently, but by the time they merge onto one by the time the two supplies of aircraft engines get to you, they've been mixed together, and so you can't tell anymore which aircraft engine came from plant 1 and which aircraft engine came from plant 2. And you don't even know if there are two plants, right? You just see the stream of aircraft engines, you're hypothesizing that there are two types. And so in every iteration of EM, you're taking each aircraft engine and guessing, for this one, I think there's 8% chance it came from process 1 and 20% chance it came from process 2. So that's the E step. And then in the M step, you look at all the engines that you're kind of guessing were generated by process 1, and you update your Gaussian to be a better model for all of the things that you kind of think were generated by process 1. And if there's something that you're absolutely sure came from process 1, then it has a weight of 1, close to 1 in this. But if you think there was something that, at a 10% chance coming from process 1, then that example is given a lower weight in how you update the mean for that Gaussian. Make sense? All right, cool. All right. So, it's about 33 minutes. Yeah. Okay, cool. All right. Well, I still remember when I was an undergrad doing a summer internship at AT&T Bell Labs, and someone a few offices down had learned about EM for the mixture of Gaussians for the first time. He was running on his computer, and he was going around to every single office saying, "Oh my God, you got to check this out. This is unbelievable. Look at what this algorithm can do for fitting mixtures of Gaussians." So, I mean, it shows you those are the type of people I hang out with. All right. So in order to derive, so just slightly hand-wavy arguments, like, oh, let's guess the values of the z's. Let's just have these weights and plug them into maximum likelihood. What I'd like to do is give a more rigorous derivation for why EM algorithm is a reasonable algorithm and why it's a maximum likelihood estimation algorithm and why we can expect it to converge. And it turns out that rather than just proving that this is a sound algorithm, what we'll see on Wednesday is that this view of EM allows us to derive EM in a more correct way for other models as well, the mixtures of Gaussians. On Wednesday, we'll talk about a model called factor analysis that lets you model Gaussians in extremely high dimensional spaces. Where if you have 1,000-dimensional data but only 30 examples, how do you fit a Gaussian into that? So we'll talk about that on Wednesday. And it turns out this derivation of EM we're going to go through now is crucial for applying EM accurately in problems like that. Okay, so in order to lead up to that derivation, let me describe Jensen's inequality. So let f be a convex function. To do EM, we're actually going to need concave functions. So it'll be all minus of everything, but we'll get to that in a second. But so a convex function means the second derivative is greater than 0, or in other words, it looks like that, right? So that's a convex function. Let x be a random variable. Then f of the expected value of x is less than or equal to the expected value of x. Okay? Now, maybe here's an example, right? So here's a let's see, there's the function f of x, And let's say that these are the values 1, 2, 3, 4, 5. And suppose that x is equal to 1 with probability 1/2 and is equal to 5 with probability 1/2, right? Just for illustration. Then here is f of 1. Here is f of 5. Here is f of 3. And f of 3 is f of the expected value of x, right? Because so the expected value of x, and sometimes I write this without the square brackets, right? Is the average of x is equal to 3. And so the expected value, f of the expected value of x is equal to this value, whereas the expected value of f of x is the mean of f of 1 and f of 5. Right? So the expected value of f of x is a 50% chance of being f of 1 and a 50% chance of being f of 5. And so the expected value of f of x is equal to this value in the middle. It's really take these two, right? Take this value and take the mean. So it's this value up here. And this value is the expected value of f of x. Okay? And so in this example, the expected value of f of x is greater than f of the expected value of x, right? As predicted by Jensen's inequality. I'm going to just draw one illustration that may or may not help. Some of my friends like it. I sometimes use it, but if it's confusing, then don't worry about it. But it turns out that if you draw a line that connects these two, then the midpoint of this line is the height of f of expected value of x, right? So the height of this, so given these 2 points, this point and this point, if you draw this line, it's called a chord, then the height of this point is expected value of f of x. And this point is f of the expected value of x, right? And in any convex function, really take any convex function, that's also a convex function. If you draw any chord, that green point is always higher, right, than that group green point, which is another way of seeing why Jensen's equality holds true. Okay, if this visualization doesn't help, don't worry about it. But just actually, what a lot of my friends do is we keep on forgetting which direction Jensen's equality goes. Like when we're using this, that's not great. So a lot of my friends, when we don't remember, we draw this picture and draw that chord, and then we quickly figure out which way the equality goes. All right, so. One addendum, further, if f is strictly greater than 0, and so if this is the case, we say f is strictly convex, then so let's see, a straight line is also a convex function, right? So this is a convex function, this is a convex function, this is a convex function. Turns out a straight line, that's also a convex function. But so in this addendum, it's saying that if f is a strictly convex function, meaning basically it's not a straight line, right? And a bit more than it's not a straight line, but if the curvature, if it's always bending up, then the only way for the left and right hand sides to be equal is if x is a constant, meaning it's a random variable that always takes on the same value. Okay, so Jensen's equality says that left-hand side is got to be the same as right-hand side. Sorry, I think I reversed the order of these two for that equation, but it doesn't matter, right? But so Jensen equality says left-hand side is always less than or equal to the right-hand side, and the only way it's equal is if x, is a random variable that always takes on the same value. Okay, yeah.
What if the value of f of 1 was equal to the value of f of 3? Wouldn't that?
Yeah, so it turns out, what if value of f1 is equal to value of f3?
It turns out that's
So let's see. So one way that could happen would be if the function were like that, and then if you draw the chord, take the mean is still higher.
I mean, if the point of f of 1 was horizontal, the point of f of 3.
Then it's important, if you had a flat part here, then the function is not strictly convex. And so it's still less than or equal to, but it can't be equal to if x is random. Okay? So, and we'll use this in a little bit. We'll actually end up using this. Again, for the strict probabilistic, for those of you that, I don't know, take classes in advanced probability, the technical way of saying x is a constant is x is equal to ex with probability 1. You know what? I think for all practical human purposes, you do not need to worry about this. But I think if you take a class in measure theory, the professor in measure theory will be happy if you say this and you say x is a constant. But maybe none of you are. Okay, yes, don't worry about it. Oh yes. Okay. Now, just one more addendum to this is that the form of Jensen's equality we're going to use is actually a form for a concave function. So instead of convex, I'm going to say concave. And so, a concave function is just the negative of a convex function, right? If you take a convex function and take the negative of that, it becomes concave. And so the whole thing works with everything flipped around the other way. Yeah, yep, and so f is strictly concave. Okay. So the form of Jensen's equality we're going to use is actually the concave form of Jensen's equality, and we're actually going to apply it to the log function. So the log function, right, log x looks like this, and so that's a concave function. And so the inequality we'll use will be in this direction, to have in orange. All right. So here's the density estimation problem, meaning density estimation means you want to estimate P of x. Right? So we have a model for P of x comma z with parameters theta. And so, instead of writing out mu sigma and phi, like we did for the mixture of Gaussians, I'm just going to capture all the parameters you have, whatever your parameters are, I'm just going to capture them in one variable, theta. And you only observe x. So your training set looks like that. So the log likelihood of the parameters theta is equal to sum over your training examples log P of xi parameterized by theta. And this in turn is log of sum over z P of xi zi parameterized by theta, right? Because P of x, is just taking the joint distribution and summing out, marginalizing out zi. Okay. And so what we want is maximum likelihood estimation, which is to find the value of theta that maximizes this log likelihood. Right? And what we'd like to do is derive an algorithm, which will turn out to be the EM algorithm, as an iterative algorithm for finding the maximum likelihood estimate of the parameters theta. So let me draw a picture that I'd like you to keep in mind as we go through the math, which is, the horizontal axis is a space of possible values of parameters theta. And so there's some function L of theta that you're trying to maximize. That's fine. And so what EN does is, let's say you initialize theta at some value, maybe randomly initialize, similar to the k-means cluster centroid, which is randomly initialize your mu's for the mixture of Gaussians. What the EM algorithm does is, in the E step, we're going to construct a lower bound, shown in green here, for the log likelihood. And this lower bound, this green curve, has two properties. One is it is a lower bound, so everywhere you look, over all values of theta, the green curve lies below the blue curve, so it is a lower bound. And the second property that the green curve has is that it is equal to the blue curve at the current value of theta. Okay? So what the E step does, which we'll see later, and just keep this picture in mind as we go through the E step and the M step, is it'll construct a lower bound that looks like this, right? Oh, and also to foreshadow part of the derivation, right? There was that addendum to Jensen's inequality where we said, well, under these conditions, it holds with equality, right? E of f of x equals f of e of x. We said, well, the two things are equal under certain conditions. We want things to be equal. We want the green curve to be equal to the blue curve at the O value of theta. So we'll use that addendum to Jensen's inequality when we derive that. So that's E step, is draw the green curve. And then what the M step does is it takes a green curve and it finds the maximum. Right. Sorry, let me still draw it in green. What the M step does is it takes a green curve and it finds the maximum. And one step of EM will then move theta from this green value to this red value. Okay? So the E step constructs the green curve, and the M step finds the maximum of the green curve. And this is one iteration of EM. The second iteration of EM, now that you're at this red thing, is we'll construct a new lower bound. And again, it's a different lower bound. Everywhere the red curve is below the blue curve, and the values are equal at this new value. That's the E step. And then M step will maximize this red curve, and so on. Now you're here, construct another thing, do that, right? And you can kind of tell that as you keep running EM, this is constantly trying to increase L of theta, trying to increase the log likelihood until it converges to local optimum. Okay. The EM algorithm does converge only to local optima, so if there was another even bigger thing there, then it may never find its way over to that other better optimum. But the EM algorithm, by repeatedly doing this, will hopefully converge to a pretty good local optimum. Okay? All right. So let's write out how we do that. Let me think. Actually, let me use the new board. No, maybe it's okay. All right. So I've already said that our goal is to find the parameters theta that maximize this. Right? And so that equation we said just now is sum over I log sum over zi P of xi, comma zi, given theta. Okay, so this is just what we had written down, I guess, on the left. What I'm going to do next is divide by, multiply and divide by this. Okay. Where Qi of Zi is a probability distribution. i.e., sum over Zi, Qi of Zi equals 1. Okay? So I'm going to multiply and divide by some probability distribution. And we'll decide later how to come up with this probability distribution Qi, right? But you know, I'm allowed to construct a probability distribution and multiply and divide by the same thing, right? Now, if you look at this, all right, let's put square brackets here. If these Qi's, if this is a probability distribution, meaning that sum over Zi, Qi of Zi sums to 1, then this thing inside is equal to sum over I log of an expected value of Zi drawn from the Qi distribution of actually, maybe if I let me use colors to make this clearer. Right? So the way you compute the expected value of, you know, some function of Zi is you sum over all the possible values of Zi, of the probability of Zi times whatever that function is. So this equation is just the expected value with respect to Zi drawn from that Qi distribution of that thing in the square brackets, in the purple square brackets. Now, using the concave form of Jensen's inequality, we have that this is greater than or equal to So this is a form of Jensen's equality where f of E x is greater than or equal to E of f of x, where here this is the logarithmic function, right? So the log function is a concave function. It looks like that. And so using the, I guess, you know, using the form of Jensen's equality with the signs reverse, right? F of Ex is greater than or equal to E of Fx, so you get log of expectation is greater than or equal to expectation of the log. Okay? And then finally, let me just take this expectation and unpack it one more time. So this is now sum over I, sum over Zi, so I just took this expected value and turned it back into sum over random variable, probably times that thing. Okay. So if you remember this picture from the middle, what we wanted to do was to construct a function, construct this green curve, there's a lower bound for the blue curve. And if you view this formula here as a function of theta, right? So your x is just your data, and z is a variable you sum over. So this whole thing is a function of theta, right? Because x's are fixed, z is just something you sum over. So this whole formula here, this is a function of the parameters theta. And what we've shown is that this thing, you know, this formula here, this is a lower bound for the log likelihood for this thing. Right? I guess this is L of theta. Right? So, go ahead. Oh, how we got to this equation? Sure. Let me think. So, let's see. Let's go and do this. Let's say that z takes on values from 1 through 5. Right? Let's say z takes on values from 1 through 10. So you roll a 10-sided dice. And I want to compute the expected value of some function of some function g of z, right? Then the expected value of g of z is sum of all the possible values of z, of the probability that you get that z, times g of z, right? So that's what the expected value is of a function of a random variable, right? And the expected value of z is sum over z, p of z times z, right? That's the average of a random variable. And so in the notation that we have, the probability of z taking on different values is denoted by qi of z, which is why we wind up with that formula. Does it make sense? No? Does it? Okay. Is that okay? Does it make sense? Yeah. All right. If one of these steps doesn't make sense, let me know. Do you have other questions? Okay. All right. Hope that makes sense. Now, one of the things we want when constructing this green lower bound is we want that green lower bound to be equal to the blue function at this point, right? And this is actually how you guarantee that when you optimize the green function, by improving on the green function, you're improving on the blue function. So we want this lower bound to be tight, right? To be the two functions to be equal, tangent to each other. So in other words, we want this inequality to hold with equality. So we want, so we want the left-hand side and the right-hand side to be equal for the current value of theta, right? So on a given iteration of EM, with the current parameters equal to theta, we want I know this is a lot of math, but we want the left and right hand sides to be equal to each other, right? Because that's what it means for the lower bound to be tight, for the green curve to be exactly touching the blue curve as we construct that lower bound. And so for this to be true, we need the random variable inside to be a constant. So we need p of xi zi divided by qi of zi to be equal to a constant. Right? Meaning that no matter what value of zi you plug in, this should evaluate to the same value. In other words, the ratio between the numerator and denominator must be the same. And fortunately, so far, we've not yet specified how we choose this distribution for zi. Right? So far, the only constraint we have is that qi has to be a probability density, has to be a probability distribution over zi, but you can choose whatever distribution you want for zi. And it turns out that we can set qi of zi to be proportional to p of xi zi parameterized by theta. And this means that for any value of z, so z indicates is it from Gaussian 1 to Gaussian 2, right? So this means that the chance of Gaussian 1 is proportional to the chance of Gaussian 1 versus Gaussian 2. Whether zi takes on 1 or 2 is proportional to this. And I don't want to prove it, but one way to ensure this, and this is proven in the lecture notes, but it turns out that one way to ensure, so the QIs need to sum to 1. So one way to ensure that this is proportional to the right-hand side is to just take the right-hand side. Sorry, right in here. So let's see. Right, so the QIs have to sum to 1. And so one way to ensure the proportionality is to just take the right-hand side and normalize it to sum to 1. And after a couple steps that in the lecture notes, but I don't want to do here, you can show that this results in setting qi of zi to be equal to that posterior probability. Okay. And so, sorry, I skipped a couple steps here. You can get from the lecture notes, but it turns out that if you want this to be a constant, meaning whether you plug in zi equals 1 or zi equals 2 or whatever, this evaluates the same constant. The only way to do that is to make sure the numerator and denominator are proportional to each other. And because qi of zi is the density that must sum to 1, one way to make sure they're proportional is to just set this to be with the right-hand side but normalize the sum to 1. Okay? And we derive this a little bit more carefully in the lecture notes. So, just to summarize, this gives us the EM algorithm. Let's take all this, everything we just did and wrap into the EM algorithm. In the E step, we're going to set qi of zi. Right, equal to that. And previously, this was the Wij's, right? So previously, we're storing these probabilities in the variables you call Wij's. And then in the M step, we're going to take that lower bound that we constructed, which is this function, right, and maximize it with respect to theta. Okay? And so remember, in the M step, we constructed this thing on the right-hand side as a lower bound for the log likelihood. And so for the fixed value of Q, you can maximize this with respect to theta, and that updates the theta, maximizing the green lower bound, right? That's what the M step does. And if you iterate these two steps, then you find that this should converge to a local optima. Okay? Oh, and just maybe it begs the obvious question, why don't we try to maximize, right, theta why don't we try to maximize the log likelihood directly? It turns out that if you take the mixture of Gaussian's model, try to take derivatives of this and set derivatives equal to 0, there's no known way to solve for the value of theta to maximize the log likelihood. But you find that for the mixture of Gaussian's model and for many models, including factor analysis, which we'll talk about on Wednesday, if you actually plug in the Gaussian density, if you actually plug in the mixture of Gaussian's model for P, and take derivatives, set derivatives equals 0 and solve, you will be able to find an analytic solution to maximize this M step, and it'll be exactly what we had worked out in the early derivation of the EM algorithm. Okay, but so this derivation shows that the EM algorithm, is a maximum likelihood estimation algorithm with optimization solved by constructing lower bounds and optimizing lower bounds. Okay, all right. That's it for today, and only stuff up to here, right? And so this stuff will be up to the midterm, but we'll talk about on factor analysis. We're not on Wednesday. We're not in the midterm. Okay, so let's break for today, and I'll see you guys on Wednesday.